Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 13. Today we will change gears to another electronic device that is very interesting and very useful in circuit design, and that is called the bipolar transistor. The bipolar transistor is a little more complex than the diode, than the PN junction that we studied before. So as such, it requires some more patience and detailed analysis to understand how it works and what it does. Now, if you prefer to learn about CMOS circuits and devices first, the lectures here are structured such that you can skip the bipolar physics and circuit lectures and directly go to the CMOS physics and circuits videos that appear later. But if you prefer to start with bipolar, you can start with this lecture. All right, so today this is what we would like to accomplish. We will start by looking at the structure and the symbol of bipolar transistor, and then we go to its operation, its physics. In fact, the development that we follow here is similar to what we pursued for the PN junction. There we wanted to see how the device operates internally, and then what kind of model we can create for it, a circuit model, an exponential or whatever works, and then use that model and those properties that we understand to see how a device operates inside the circuit, how we formulate the behavior of the device inside the circuit. So we want to do the same thing here. First, we want to understand how it operates, its internal phenomena. Then we want to create a model for it, a model based on familiar electric devices such as current sources and voltage sources and resistors, etc. And then we want to use that to build interesting circuits. All right, now before we go there, I thought I'd take a quick look at what we did before, just to remind you of some of the functions that we need in electronic systems and how they relate to our discussion today. So let's take a look at our Circuitpedia here. So again, remember that when we designed the Bluetooth transmitter and receiver, we had an oscillator whose frequency was modulated by the ones and zeros, and then we had a power amplifier, and then on the receive side we had a low noise amplifier followed by some other processing, followed by an analog to digital converter, and then some more processing. Now if you look at what we have here, we can actually identify several places where we have amplification. Power amplifiers have amplification. Low noise amplifiers have amplification. In fact, oscillators also require amplification before they can oscillate. And even this analog to digital converter has amplification in it. So amplification is an essential and very useful operation in almost all electronic circuits. The concept of being able to amplify a signal is critical to every electronic systems that we study here. So naturally, we want to build amplifiers, and we will spend a great deal of this course on building amplifiers. So the question is, how do we build an amplifier? All right, well, I can actually show you something very simple that allows you to build an amplifier, and then we can take it from there and see how a transistor, a bipolar transistor, comes into the picture. All right, so let's do this. So let's first define what we mean by an amplifier. So what is an amplifier? Well, intuitively, we sort of know what it means. An amplifier is a black box, so we'll call it amp, which perhaps receives a voltage So we give it a voltage source here, V in, and it generates a voltage, V out. And this is what we observe. If we give it some sort of signal, like so, in a time domain, it will give us hopefully the same signal, but with a greater amplitude. So what we expect to see is something like this. A familiar example is when you're speaking to a microphone, and then this microphone signal has to go somewhere. For example, my voice is going through this microphone right here, and eventually is recorded on the video that you're watching. So this microphone generates a very small signal. So my voice is converted to electricity, but it's a very small signal. And that small signal would not suffice for recording. So we go through an amplifier and then try to record it. Okay? All right. Now, how do we build an amplifier? So let's build an amplifier. Okay, this pen is acting up a little bit. Let me erase all of this and go back to here, an amplifier. Okay. All right. So do you remember the concept of dependent sources in basic circuit theory? We said a dependent source is a source, a current source or a voltage source, whose value depends on some other quantity somewhere else. So this current source here has a value that is a function of maybe a voltage over here or a current over there. That's what we call a dependent source. So let's go and buy a particular type of dependent source. Remember that we have 4 types, because the source can generate a current or a voltage, and it can depend on a current or a voltage. So I will buy one particular type. And in our circuit theory courses, typically we draw a dependent current source by a diamond to distinguish it from an independent current source with an arrow in it. So I'll go by this current source, which has a value, we'll call it I1, and I1 happens to be some factor times a voltage. And that voltage happens to be here, V1. Okay, so I buy this device. This is a voltage-dependent current source. It's a current source, and its value depends on a voltage. So we call it a voltage-dependent current source. Sometimes we call it a voltage-controlled current source. Same thing. Voltage-controlled or voltage-dependent current source. This current source has a value that is K times V1. Why do we need K here? Well, to make sure that the dimensions work out. This is a current. It has a dimension of current, a unit of ampere. This is a voltage. Has a dimension of volt. Voltage has the unit of volts. So to go from volts to current, I need some unit here. All right, so we bought this voltage-dependent current source. And I'm hoping to build an amplifier. So I will connect my input source to here. That is the input. This input, for example, that sinusoid or my voice that goes into this microphone. And then I take these 2 wires and connect them to a resistor. And we call this resistor for now RL. That's it. And I claim that this circuit here, from here to here, can serve as an amplifier and amplify this signal and produce it here. So the voltage across this resistor will be our output signal, And we are hoping that V out will have larger excursions, larger swings than the input. So let's go ahead and check and see if that's true. Okay, well, how do I analyze the circuit anyway? This is very simple from circuit theory point of view. You have analyzed much more complex circuits. What I will do is write a KCL at this node. I have two currents, this current, and nothing else. So this current plus this current has to be 0. This is not going anywhere, so there's no current there. How much is the current through RL? Well, voltage over resistance, so V out over RL. So we have V out over RL. And then how much is this current? This current is KV1 plus KV1 must be equal to 0. Now, do we know how much V1 is? V1 is this voltage that is inside the device. But all we've done is we just connected two wires to the input. And because the wires are ideal wires and there's no current anyway, this voltage must be equal to this voltage, right? It's just like you took a battery and connected two wires to it, so you should still measure the battery voltage. So V1 is actually the same as V in. So let's replace V1 with V in, and let's try to find V out, because we are interested in the output voltage. So this says that V out is equal to minus KV in times RL. So minus KRL times V in. Can this be an amplifier? So let's say I choose K, the property of this voltage-dependent current source, times RL to be some number, like 5. So let's say this whole thing happens to be minus 5. So what we have is V out is equal to minus 5 V in. Would you consider this an amplifier? Well, if you draw the waveforms, we might see it better. So we draw our input again in red. So here's our input waveform, V in. And what does our output waveform look like? Our output waveform is minus 5 times this. So it means take the amplitude, multiply by 5, but then flip the sinusoid because we have a negative sign here. So for V out, we have the following shape. We have T, and I just take this, magnify it by a factor of 5, and then flip it. So it goes like this and goes like this. So that would be V out. Well, for all practical purposes, this is an amplified version of this. And the fact that it has a negative sign here, the fact that it's flipped, hardly matters. In almost any application, we can live with this negative sign. It doesn't bother us. So this circuit is indeed an amplifier. So we can build an amplifier like that. The only thing is that we have to buy a voltage-dependent current source. Now, if you go to your electronics store and say, can I have a voltage-dependent current source? The reaction will be, what? Because they don't know what that is. So we have to figure out how we can implement this using devices that are known to us. Resistors cannot do it, inductors cannot do it, transformers maybe, capacitors cannot do it, diodes cannot do it, so we need a new device, and that device is a transistor. We can have a bipolar transistor do this, or we can have a MOS transistor do this. And for this lecture and a number of lectures that follow, we are focusing on the bipolar transistor. Okay, so now we are ready to go to the bipolar transistor, and we start with the structure and symbol. So structure and symbol. Actually, sorry, let me do something else before I go there. I want to talk about a few other concepts before we go there. So, all right, so before we jump into the bipolar device, I need to refresh your memory about a few concepts that we have seen before and just make some other observations. So please be patient for now and let's do this. Okay, so a few observations. These are really from the p-n junction studies that we have done before. Okay, so number one, concept of carrier injection. Let's take a p-n junction, as we know, and reverse bias it. So here's our p-n junction. So for example, N on the left, P on the right. We have a depletion region here. So we have some positive ions on this side, some negative ions on this side. We have a battery to give us the reverse bias. So positive on the left, negative on the right. So that's a reverse biased p-n junction. Now, let's say that magically we can inject electrons into the structure from outside. In fact, we want to inject the electrons right here, right into this depletion region on the p side. So if I bring some electrons from outside and inject them into the depletion region on the p side, right here, what happens to those electrons? Well, you have to remember what the electric field looks like. The electric field in this region is pointing this way, from left to right, from positive to negative. So once an electron appears inside that electric field, the electric field pushes it this way. So the electron comes out here and is absorbed, goes through the N section, and is absorbed by the battery. So if we keep injecting electrons into this region, they keep flowing through the N side and go to the battery. We have a continuous current flowing at all time as long as we have electrons supplied into that region. Now we don't exactly know how this is possible from outside, but that's okay, we'll get there. So this is what we call carrier injection into the depletion region. So we just need to remember that. We can say that if we inject electrons here, they are collected by this N section and by this battery. They don't just stay here. They go through the depletion region and are collected by this N section and the battery. All right, so the next concept that we need to talk about is effect of asymmetric doping. Again, for the p-n junction. All right, so let's take a p-n junction and this time forward bias it. So we have a p-n junction, and N here, P here. We forward bias it using a battery. And of course we have a current flowing this way, right? The current is circulating like this. And we still have a little bit of depletion region, but don't worry about that too much. Okay, so we have a forward biased junction. And the question is, how much of the current is carried by electrons and how much of the current is carried by holes? What we do know is that the electrons start from the N section and go this way to go to the positive side of the battery, and the holes start from here and go to the left. Now, what if I have heavily asymmetric doping, meaning that, for example, I have a very high doping level here and a low doping level here? What happens? Well, if I have a high doping level here, which I will call heavily doped. So remember, in here, the doping is denoted by N sub D, donor density. So let's say donor density is very high, 10 to the 17 per cubic centimeter. And let's say that this side has only small doping, so we call it lightly doped. And so this would be acceptor density, and the assumption that the acceptor density is small, maybe 10 to the 15. So maybe this is 100 times this, right? So then what do we expect? Well, we have lots of free electrons here. So they would like to travel to the right and carry the current. But we don't have that many holes here. So we have some holes, and they do carry this way. They go this way and carry the current. So what we are thinking is that when this situation exists inside the p-n junction, we end up with lots of electrons going this way. So these are all electrons. And just a few holes going the other way. So we have just a few holes going this way. For example, for every 100 electrons that go this way, only one hole goes this way. The junction is still forward biased and the current is flowing, everyone is happy, but there's a significant difference between the current of electrons and the current of holes. So we need to remember that when we go to the bipolar transistor and study it. Okay, so now let's go and look at the structure and symbol of the bipolar transistor. So structure and symbol. All right, the bipolar transistor is very interesting. It has 3 semiconductor sections and therefore 3 terminals. Remember, for a p-n junction we have only 2 terminals, 2 sections. But for a bipolar transistor we have 3. So it's a little more complicated now. Here's what it looks like. We have, for example, an N section, a P section, and another N section that are attached to each other like this. So there's a junction between these two, and there's a junction between these two. And of course we need terminals to access these from outside. So for now, let's say there's a terminal here, there's a terminal here, and there's a terminal here. So we have attached wires to these 3 sections. All right. Okay. Is this device symmetric? Meaning, can I flip these 2 up and down? Well, no. In reality, it's not. In reality, actually, what happens is that we want to have this asymmetric behavior here. So we will make this bottom guy heavily doped, but not this top guy. So the bottom section, the bottom N section, will be heavily doped. Now, how do we make sure that we don't get confused? Do we just write heavily doped every time? Well, we have a little symbol to make sure that people understand. So I will put a plus here, and that means this is heavily doped. So obviously you can see that the device is no longer symmetric around this axis. All right, we also have to give names to these terminals. Remember that for the diode we said this is the anode and this is the cathode. Well, here it's different. We don't call it those anymore. So we call this terminal, the bottom terminal, emitter, or E for as an abbreviation. We call this one the base, or B, and we call this the collector, or C. Okay, so that's simple enough. I might expect from these names that something is interesting happening. The emitter emits. What does it emit? Charge, maybe electrons. The collector collects. What does it collect? Charge, maybe electrons. So maybe what's happening is that electrons start from here and go here. Is that good? Well, a piece of wire would do the same thing. So why is this better than a piece of wire? Well, there's a third terminal here, and this third terminal does something interesting. So that's what you need to study and understand. All right, so just a historical note, the bipolar transistor was invented by, let's see, I want to do this, was invented by William Shockley and two colleagues at Bell Laboratories back in 1940s. So here are their pictures, and here's what the device looks like. It's very crude, it looks very primitive by our standards today. So you can see that there's a contact here, there's a piece of wire here, there's another piece of wire here, there's a contact here. And there are some other wires out here. This is, of course, zoomed in to see what it looks like. And this is called the bipolar device. Now, when the bipolar junction transistor was invented back then, it wasn't very good. In fact, it was not even made of silicon, it was made of germanium. But the fact that for the first time they saw this device can amplify was indicative of a revolution. Because before that, we did not have anything else. We did not have such compact devices that could amplify. We had vacuum tubes that could amplify, but the vacuum tubes were big. They were about this size. So if you wanted to build an electronic device like a radio, you would have to have lots of these vacuum tubes in there. It was very difficult and very cumbersome. So this was why we had, there was so much excitement about this, and eventually why it found its way into everything that we built. Okay, now for this device, we can envision a symbol. Remember, for the diode, we did not go around and draw this all the time in our diode circuits. We had a symbol. So maybe for this one, we also have to have a symbol. Now, historically, it's also interesting that I can show you when we look at the circuits from back then, when the transistor was invented, we see certain things like this. This is a patent from Shockley himself, filed in 1952, and these are some circuits using the bipolar transistor. You see N, P, N, or even diode NP. I guess back then they did not have these symbols for these structures yet, so they would literally draw them like these and then show, here's one circuit, here's another circuit. They call them bistable circuits, etc. But today, fortunately, we do have symbols, so we don't have to do that. And I'll show you the symbol for the bipolar transistor. Okay, well, we have three terminals. So here's a bipolar transistor with three terminals. This is the emitter, this is the base, this is the collector. Okay. You can see that this symbol is also asymmetric, and this arrow is what distinguishes the emitter from the collector. So there's always an arrow on the emitter terminal. Now, whether the arrow points outward or inward depends. For now, we are using this structure, and for this structure we have this symbol. In fact, this is called an NPN transistor. So, and this is the symbol for it. So it's called an NPN transistor. So you might be guessing that there's another version, right? There could be also, these could be P and this could be N. So that we could have a PNP transistor. But all in good time. For now, we just focus on this. All right. So, now suddenly the world looks much more overwhelming. We are used to studying circuits that use primarily two-terminal devices. Diodes, resistors, capacitors, inductors. We have transformers, but that's a different story. Now suddenly, we have a device with 3 terminals. So that looks pretty complicated. We can have a voltage from here to here, voltage from here to here, voltage from here to here. There are all possible combinations of voltages. Which one should be positive, which one should be negative? For a diode, we saw that, okay, if this side is more positive than this side, we are in forward bias, and the other way around. But here, my God, what do we do? Okay, no problem. We'll take it one by one. The good news is that only one combination of voltages around this device actually makes it a useful device. There are many other combinations, but they're not very useful, so we don't even have to think about them. The combination that we will be using is as follows. So, in our studies, this is what we assume. We assume that this junction is forward biased. So this junction is forward biased. Okay? And we assume that this junction, you can see there's another junction here, right? This junction is reverse biased or has zero bias across it. So 0 or reverse. So I will write here 0 or reverse bias. All right? Okay. So under these two conditions, forward biased junction between the base and the emitter, between the base and the emitter, and reverse or zero bias, so reverse biased between the collector and the base, that's a combination that we would like to use this device in. That's when it becomes an amplifying device. Okay, so under what condition is the junction forward biased? Well, P should be positive with respect to N. So base should be positive with respect to emitter. So this point has to be positive with respect to this point. By how much? 700 to 800 millivolts. Right? That was the voltage that we said is a typical value for PN junctions to be forward biased and have some reasonable current in them. All right, how about the other junction? This junction must be reverse biased or have only zero bias. It cannot be forward biased. Okay, so that means that N has to be more positive than P, or they just have to have the same voltage. So generally we can say that this should be reverse biased. So this terminal should be more positive than this terminal. This is N, this is P, so N should be more positive than P. Or they can have a zero difference. So it's good to remember these polarities here, because that's the condition under which we will use this transistor. When both of these conditions are satisfied, we have a name for that region of operation. We say this is active forward bias. So active forward bias means that these conditions have to be met. So I will circle them. This condition and this condition result in this general region of operation. All right, so when we say forward active bias, active forward bias, or sometimes we just say active forward bias, active bias, that's what it is. Sometimes, in fact, we don't say bias, we say region. So I will write that also as active forward region. You may even see forward active region, all sorts of combinations, doesn't matter. The key is active. Okay, so we are gradually easing our way into the device, its symbol, some of the conditions around it, etc. We still have no idea what the device does, but at least we have a picture of it and we have a symbol for it. So step by step. Now, the other point that I wanted to raise here is that now that you know p-n junctions very well, if you look at this, you say, well, I have a diode from here to here, and I have a diode from here to here. So maybe this is just like this. Maybe I can say that this is equivalent to, I have a diode from here to here, P-N, anode, cathode. So let me draw that here, anode, cathode. And there's another diode from here to here, anode, cathode. So here's another diode here. Right? So actually I don't need to buy a bipolar transistor from the market. I can go buy two diodes and hook them up like this, and that should operate as a bipolar transistor. But unfortunately that is not true. So this is not true, and this is not a bipolar transistor. So as we study bipolar transistors, we will see that this would not operate as that. So that's a word of caution, not to get confused between this and this, even though they look very similar. All right. So one last point before we go on. The last point that I wanted to raise here is the following. The base region is very thin. By base region, we mean from here to here. This is very thin. The distance between this junction and this junction is very short compared to this distance, or compared to the distance between this terminal and the center of this, if you want to define some sort of distance. All right, we will see what that means and what the implications are when the base region is thin. That's an essential property that we need for the bipolar transistor to operate properly and as an amplifying device. All right, so with these preliminary considerations, we can now go and talk about the operation of the bipolar transistor. So we want to go inside here and study what's going on. When I have a forward bias according to what I said before, and maybe a reverse bias here, what happens? Well, forward bias means there's a current flowing, so that's good. Reverse bias means no current flowing. Well, that wouldn't be that good. So something else must be happening that makes this device interesting and useful. So we have to understand that. So let's go ahead and add another page here. And then we can go and start into the bipolar transistors. Okay, so let's go to operation of bipolar transistor. So we want to understand the physics of the device. All right, so first thing I need to do is create those conditions. Remember, the base emitter must be forward biased, and the base and collector junction must be reverse bias or have zero bias. So you can see that I'm using this name now. So let me go back here and make sure that we are familiar with this name. So from now on, we will call this the base emitter junction. I will call this the base collector junction, or collector base junction, doesn't make any difference. But one more point is that we will call this the base emitter voltage, and this one base collector voltage, or if you like, collector base voltage. So these are the names that we will be playing with. All right, let's go back and start digging into the device. All right, so here's what we have. Let's draw the symbol first. Drawing the symbol is a little easier for now, and then eventually we draw the structure as well. So I would like the base emitter to be forward biased. So I connect the battery from here to here, plus, minus. Right? Now the base is more positive than the emitter by how much? Let's say 800 millivolts. So we have 0.8 volts here. We will call this the base emitter voltage, VBE. Base emitter voltage. So base is more positive than the emitter. All right, now let's say that I would like the base collector junction to be reverse biased. So I will probably connect a battery there too. So let's go ahead and connect the battery here. And if I want to create a reverse bias, it has to be like this. Because remember, this is N, this is P, this is N. So for reverse bias, for N to P, I need positive to negative. Right? So maybe that's how I should connect my batteries to make sure that the device is in the forward active region. Okay, well, it turns out that if we do it this way, the result will not be very useful. So we will see that maybe a week from now, or some lectures from now. But I have to make a small change here for these conditions so that this device actually becomes useful as an amplifying device later. So I will make a change like this. The base emitter is still the same. So here's the base and the emitter connected by a battery, which we call VBE. But instead of connecting a battery between the collector and the base, I will connect a battery between the collector and the emitter. So I connect the collector like this. And I will call this VCE. So that's a little different, right? These two circuits are not the same. But this will do what we want, and eventually it will also allow us to amplify and other things. So how do we make sure that we still have proper conditions? Proper conditions meaning base emitter is forward biased. That's good. We have a battery, no problem there. But how about collector emitter? Am I sure that collector emitter is reverse biased or has zero bias? Well, that's not that hard. What I can say is that this voltage, which is the voltage of interest to me, and I will call it VCB, collector base, can be obtained using KVL. We have VCE, this voltage, is equal to this voltage plus this voltage, right? We have a loop around. So we can say that VCB is equal to VCE minus VBE. And because I want VCB to be 0 or higher, 0 or reverse bias, so this has to be greater than or equal to 0. That means that VCE has to be chosen to be this much. So for example, if VBE is 0.8 volts, if this is 0.8 volts, then this has to be 0.8 volts or higher. The higher it is, the more reverse bias we have from collector to base. All right, so this is the topology, the environment in which we will study the bipolar transistor. Okay. All right, so let's draw the bipolar transistor again. This time it's actual structure, and see what's going on inside this device. It's an ingenious invention when we understand it. So it's good to look at it carefully. We said that the emitter is heavily doped, so we call it M+, and we have a battery connected between the base and the emitter. So I have to erase this and go back here. All right, so we have a battery connected between the base and the emitter. So that's what we call VBE, and is positive enough to create a forward bias. And then I have another battery connected between here and here. And this battery is also positive, more than 0.8 volts, and we call that VCE. Okay, so here's what's going on. Well, remember that the base emitter junction is forward biased. So this is forward biased. That means there's current in it, right? We have current in this loop. Now the question is, what constitutes this current? Electrons or holes? Or if you look at it, which carrier is more dominant? Well, we have M plus here and P here. So we have lots of electrons going this way and some holes going this way. So I will draw that. So we have lots of electrons. I will draw that by lots of arrows going this way. These are electrons going that way, and then some holes going this way. This is deliberate, right? We pick this to be heavily doped. That's why we have lots of electrons going that way and just a few holes going this way. So again, as an example, we could have 100 electrons going this way for every hole that goes this way. Now the current is going on all the time. So we measure it, we see that the current of electrons is maybe 100 times the current of holes, as an example. Okay, very good. But then, is that it? In other words, if this junction is reverse biased, does it mean that it has no current? If it has no current, then that's open, this is not useful. So something else must be going on. All right, well, we have a reverse biased junction here by proper choice of this voltage, right? Okay, so a reverse bias junction has a depletion region. So here's a depletion region that we have between the collector and the base. All right, so what happens to these electrons that are coming from the emitter into the base? Well, they have two routes. They can either go this way to the depletion region, and then who knows? Or they can go this way through the base and to the battery. The question is, which one do they prefer? Well, they might prefer to go this way because the shorter distance, provided that they can be absorbed once they get here. If there's a good sink of electrons, if we can sink these as they arrive here, we can quickly take them away, then they prefer to go this way because this is so short. If you think about resistance, you can see that this resistance is much less than this resistance. So they prefer to go this way, if we have the ability to absorb them as soon as they get here. So let's check that. If the electrons cross the base emitter junction, and this is very thin, so they get to this edge of the depletion region, what happens to them? Well, remember the first observation I made about the injection of carriers? We said that if we place an electron here, because we have an electric field pointing this way, the electron will go that way and will go into the N section, and it will be collected by the N section and the battery. So as soon as these electrons make it to the edge of the depletion region, they see the electric field, they go to the collector, and they go to the battery. So almost all of these electrons end up going to the depletion region, going through the collector, and going to the battery. So very few of them will actually prefer to go this way. Now that is very interesting. We have a reverse biased junction that actually carries current because we are injecting some carriers from outside into its depletion region. This is not something that we would have seen in a simple diode, right? Only with an external injection into the diode could we have a scenario like this. Now this external injection is automatically provided by the emitter-base junction. Okay, so what we see is that in fact there is a significant amount of current from emitter to collector, because we have electrons coming this way, they travel through the base, they travel to the depletion region through the collector and go there. So if I go back to the structure here, what I see is that electrons are going this way. Let's see, why is my pen not working? All right, so we see that electrons are traveling this way and then end up in the collector and go that way. And that's what we get for these guys. So these are electrons going that way. If electrons go from bottom to top, the conventional current, which is associated with positive charge, is going from here to here. So equivalently, we can say a current, the conventional current, is flowing from collector to emitter. So that's very interesting, because we managed to create a current between the collector and the emitter by applying a forward bias between base and emitter and a reverse bias between collector and base, or zero bias. All right, so that's what we have so far. Now, we still have to take some steps to get to the point where we understand why this might become an amplifying device, why this might become a voltage-dependent current source, as we envisioned at the beginning of this lecture. But that's okay, we'll go slowly and understand everything. All right. So we have to answer one question. So let's look at this question and see. By what mechanism do electrons flow through the base? Drift or diffusion? We said that anytime we have a current flow, it has to be a drift if there's an electric field, there's a voltage, or diffusion if there's a gradient of concentration, meaning that we have higher concentration here, lower concentration here of free charge carriers. So we know that some current is going from emitter to base and then to collector. So there's some current right here. And what type of current is that? Is that a diffusion current or a drift current? So that's what we need to understand. All right, well, it turns out that the voltage drop in this region is very small, actually, because even though this is heavily doped, this is also moderately doped, so its resistance is not that large. So we say that base region is thin, and okay, this pen is a little unwell right now. So the base region is thin and sustains little voltage. So the voltage drop on the base region is small. If the voltage drop is small, then the field is small. So the drift current through the base is negligible. So we say negligible drift current. So that implies that the current has to be primarily by diffusion. And in fact, we can even see why diffusion is necessary for the current, even if there were some drift current. So let me show you. Let's try to turn this by 90 degrees and examine the concentration of charge carriers in it. So I will draw it like this. So I draw the base quite wide just for illustration here, but we know that that's not wide. So this is what we have. Emitter on this side, base and collector. So electrons are taking off from the emitter. These are all electrons going from left to right, going through the base, going to the collector. Okay, so now I would like to plot the concentration of charge carriers as a function of distance. So this is carrier density. So on the left edge of the base, what do we know? Well, electrons are pouring into the base from the emitter area. So we have a high concentration of electrons at this point. And how about the right edge of the base? Well, we have a depletion region here. So any electron that makes it to this point is swept away by the electric field. So we have a very low concentration of electrons here. So we have some sort of large gradient between these two. It may be linear, it may not be linear. That's not a big concern right now. But what we see is that because of the concentration difference, we must have a diffusion current inside the base. So the primary transport mechanism through the base is diffusion. All right, so that's an interesting observation about the device. Let's see what else we need to understand. Okay, one other question is, what happens if VBE increases? So remember what we did. We took a battery, connected the base emitter to forward bias it. And as a result of forward bias, we had some hole current and a lot of electron current. Now, this was maybe 800 millivolts. Now, what if I make it 810 millivolts? What do I expect to happen? Well, I have a forward bias junction, so its current has to increase. If the current increases, we have a lot more electrons going this way, and again, more holes. Both of these have to increase, but of course, we have a lot more electrons. So if you have more electrons, this time, compared to this time, 810 millivolts versus 800 millivolts, then it means that we also have a higher current coming out of the collector. So what we expect is that the current coming out of the collector increases, right? So we say collector current increases. Does the emitter current increase? Sure, yes, this current increases. Does the base current increase? Sure, it increases. But why did I say the collector current increases only? Well, because we will see it is the collector current that plays a critical role in how bipolar transistors serve as amplifiers and other things. We are primarily interested in the collector current. And what we have seen so far is that if the base emitter voltage goes up, the collector current goes up. So can I draw something like that? So here's what I know. I have IC. This is what we call collector current as a function of base emitter voltage. And we said that if the base emitter voltage increases, the collector current increases. So all we know is this. That's all, right? We don't know whether this is a linear change or what. We don't know where it goes. We don't know where it starts. But we just have intuitively one little segment of this plot. So that's fine for now. That's all we need to know. But that's another observation. Okay. All right. So the question we have to answer is, what is the relationship between IC and VBE? This plot here. What does it do? Is it a straight line? Is it something else? And it turns out that what makes the bipolar transistor beautiful is that the relationship between the current in the device, this current, electrons going this way or positive charge equivalently going this way, and this voltage, base emitter voltage, is an exponential relationship. So it turns out that this is an exponential relationship, and it's just given like this by IC is equal to IS exp of VBE over VT minus 1. This is, of course, similar to that of a diode. And is it really surprising that we have the same thing? Probably not. Intuitively, we would have expected this, because when we said that we increase the base emitter voltage and this current increases, this current is the current of a diode, the current of a PN junction. So this current between the emitter and the base has an exponential dependence upon this base emitter voltage. And it is this current of electrons that ends up through the collector. So we would have expected that the current of the collector also has an exponential dependence upon the base emitter voltage. So it's not surprising that we have this expression. We are not proving it here, but intuitively this is what we would expect. All right, our time is up. Next time we will start from here and develop all sorts of interesting insights into what a bipolar transistor can do, and eventually how it becomes a critical component in circuits, for example, amplifiers. I will see you next time.